Today, we're diving into one of the most fascinating discoveries in the history of physics, the story of X-rays. From accidental discovery to revolutionizing medicine, this is a journey you don't want to miss. So hit that subscribe button and let's get started. In today's tutorial, we'll be exploring the history and discovery of X-rays. We'll cover 5 main topics: the origin of X-rays, how high-speed electrons interact with matter, the mechanisms behind X-ray production, characteristic X-rays, and the incredible story of how X-rays were first discovered. Trust me, by the end of this video, you'll have a complete understanding of this amazing phenomenon. Let's start with the fundamentals. Where do X-rays actually come from? X-rays originate from the extranuclear part of the atom. They're produced when accelerated electrons are suddenly stopped or deflected from their path due to collisions. When highly accelerated electrons lose their energy, whether it's their whole energy or just part of it, X-rays are generated. There's a mathematical relationship for this, and it's given by this formula: F equals 1.1 times 10 to the power of -9 multiplied by Z and V. Here, Z is the atomic number of the target material, and V is the voltage in volts. This factor tells us how much of the electron's energy gets converted into X-rays. Keep this formula in mind. We'll see it in action later. Now, let's talk about how these high-speed electrons actually produce X-rays. Look at these circular diagrams on your screen. They represent atoms in the target material. When high-speed electrons collide with these atoms, several things can happen. First, we have excitation and de-excitation. That's when electrons in the atom jump to higher energy levels and then fall back down. Second, we have ionization. That's when electrons are completely knocked out of the atom. Third, and this is really important, we get characteristic radiation. This happens when an electron from an outer shell fills a vacancy in an inner shell, releasing energy in the form of X-rays. And finally, we need to consider the binding energy of the incident electron. This determines how much energy is available for X-ray production. All 4 of these processes work together to create the X-rays we use in medical imaging and other applications. All right, now we're getting into the experimental side of things. Let's talk about how X-rays are actually produced in a tube. When you have a gas-filled tube at a pressure of 10 centimeters of mercury, something interesting happens. You'll see irregular streaks of light accompanied by a crackling noise, almost like tiny lightning bolts inside the tube. As you reduce the pressure to 1 millimeter of mercury, these streaks broaden out into a luminous column that extends from the anode almost to the cathode. Keep reducing the pressure to 3 to 4 millimeters of mercury, and you'll notice a discontinuity near the cathode with immediate luminosity around it. This discontinuity is called Faraday's dark space. The key takeaway here is that pressure plays a crucial role in X-ray production. As pressure changes, the characteristics of the discharge change dramatically. Now we're getting to the sweet spot for X-ray production. When the pressure is reduced even further to 0.1 millimeters of mercury, another dark space appears before Faraday's dark space. This one is called Crooke's dark space. Here's what's happening. The electrons are now moving so fast that they're producing invisible radiation, X-rays. At this pressure, the conditions are just right for efficient X-ray production. And if you go below 0.01 millimeters of mercury, really low pressure now, the striations and positive columns recede toward the anode and finally disappear completely. At this point, you're in the optimal zone for X-ray generation. Remember, mm stands for millimeters of mercury, which is a unit of pressure. It's amazing how such precise control of pressure can make all the difference. Let's visualize what's actually happening inside an X-ray tube. On your screen, you can see the different components: the cathode on the left, the anode on the right, and the vacuum pump that controls the pressure. As electrons flow from cathode to anode, they pass through several distinct regions: the positive column, the striations, Faraday's dark space, and Crooke's dark space. This diagram shows how the discharge changes as pressure decreases from 10 centimeters of mercury down to less than 0.01 millimeters of mercury. Each stage has its own unique visual appearance and physical characteristics. It's like watching a transformation, from bright, chaotic lightning to focused, invisible X-ray production. Nature is truly amazing. Now, let's do some real calculations. Imagine we have an X-ray tube with a tungsten target. Why tungsten? Because it has a high atomic number, Z equals 74, which makes it great for X-ray production. Let's say this tube is operating at 120 kilovolts, which is 120,000 volts. Using our formula, F equals 1.1 times 10 to the negative 9 times Z times V, we can calculate how much of the electron energy actually converts to X-rays. Let's plug in the numbers. 1.1 times 10 to the negative 9 times 74 times 120,000. When you work this out, you get 98 times 10 to the negative 4, which equals 0.0098, or 0.98%. Wait, what? Less than 1%? That's right. Only about 0.98% of the electron energy becomes X-rays. So where does the rest go? About 99% of the electrical power supplied to the tube is converted into heat through ionization and excitation of the target atoms. That's a lot of heat we need to deal with. This brings us to one of the most critical engineering challenges in X-ray tube design: heat management. If 99% of the energy becomes heat and that heat isn't dissipated fast enough, the target will melt. Tungsten melts at about 3,400 degrees Celsius, but even tungsten has its limits. This heat production limits both the capacity and lifespan of an X-ray tube. That's why modern X-ray machines have elaborate cooling systems. Some use oil cooling, others use water cooling, and advanced systems might even have rotating anodes that spread the heat over a larger area. Without proper heat management, an X-ray tube could be destroyed in seconds. This is a perfect example of how understanding physics leads to better engineering solutions. Now, let's talk about one of the most serendipitous discoveries in scientific history. It was November 8th, 1895. Professor Wilhelm Conrad Roentgen was working late in his laboratory in Germany. After finishing his experiments with cathode ray tubes, he started to pack up for the evening. He turned off the lights but forgot to switch off his cathode ray tube, which was wrapped in thick black paper and covered with cardboard. As he moved around in the dark lab, he noticed something strange: a faint green glow coming from some crystals of barium platinocyanide sitting on a bench nearby. Roentgen was a careful scientist. He thought, "That's odd." He switched off the tube. The glow stopped. He switched it back on. The glow returned. He realized the tube must be producing some kind of unknown radiation that could pass through the paper and cause the crystals to glow. He called it X radiation, X for unknown, and the name stuck. Roentgen was fascinated by this discovery. He spent the next several weeks in his lab investigating these mysterious X-rays. He continued his experiments, reducing the gas pressure in the tube and observing the changes: the striations, the dark spaces, and the glowing columns, just like we discussed earlier. Within weeks, he had taken the first X-ray image of his wife's hand, showing her bones and wedding ring. The world was amazed, and Roentgen became the first person to win the Nobel Prize in Physics in 1901. All right, everyone, let's wrap this up with our key takeaways. First, X-rays originate from the extranuclear part of atoms when high-speed electrons are suddenly stopped or deflected. Second, the production efficiency of typical X-ray tubes is less than 1%. Third, heat management is critical for tube longevity. Fourth, the accidental discovery by Roentgen reminds us that great science often starts with curiosity. And finally, pressure variations dramatically affect X-ray production. Controlling pressure is key to creating optimal conditions. Understanding these principles is fundamental to modern radiography, medical imaging, and many industrial applications. And that's a wrap on the history and discovery of X-rays. I hope you found this tutorial helpful and informative. If you did, please give it a thumbs up, and don't forget to subscribe for more physics content.